Okay, so good morning, everybody. Today we have the pleasure to have a couple of Bercini from Daisy with a seminar about the ThreePoint function in n equals 4 superunions and separation of values.
Yeah, I think we all really appreciate the invitation, and yeah, let's keep it informal. Like, I appreciate as many questions as you want, and I have a very small goal, so we have time to discuss if there is any questions or anything. Okay, I'll talk about this 3-point functions in n equals 4 superunions and separation of variables. And the goal is, let's try to develop some easy and powerful framework to study these 3-point functions n equals 4 superunions. So one could claim that like it already exists a framework to study, to achieve this, to evaluate or to compute these 3-point functions, and it's called hexagons. And indeed, there are. But if we compare the technology that we have, if we compare the technology that we have of 3-point functions with the technology that we have for 2-point functions, we see that this technology is a bit, they are a bit different. For example, for 2-point functions, there is this quantum spectral curve where people can compute the anomalous dimension of single trace operators up to basically any value of the couple. But for 3-point functions, when you use these integrable hexagons, besides some simplifying limits, in general, the best you can do is some weakly coupling computations. And then, for these quantum spectral curves, the central object is called the Q function. So then the central idea is basically the following. So let's try to use these Q functions, that same technology that people use to 2-point functions, to evaluate 3-point functions as well. And usually this approach of the problem is what people call separation of variables. And the main results that I'll try to present today are precisely that. So we're going to use this separation of error formalism to compute this structure constant in n equals 4 superunions, but we'll do it in a weakly couple way. So we're going to do a 3-level, 1 loop, and then 2 loops, and then we can comment a little bit how we can go to higher loops and what's the challenge that we need to go for. But so far, this is it. These are the results. But when we consider these 3-point functions, we can consider it for we will not consider for the most general operators. We'll consider for a simplified class of operators called the SO2 and SU2 operators. So the rank 1 sector operator. So let me just be a bit more precise. So the 3-point functions that we want to consider are written here. So these are the following. Sorry, I will point. I'll do a digital pointer. Sorry. So these are the 3-point functions that we need to do. So there are 2 BPS operator, 2 protected operator, and one guy is a non-BPS operator. And then you can see here, I hope you can see, they have the size big L, L1, L2, and L3. So these are the size of the 3 operators, and they are connected by all these bridges here. So there is a small L, there is big L over minus L, and then this L bottom, right? LB. One can compute these structure constants via hexagons, which I'll not comment a little bit now, but I'll comment in the end how one compute this via hexagons. And then this non-BPS operator, as I said, will not be a general operator. In fact, it will be an operator that is in these rank 1 sectors. So it's basically, it can be either SO2 or SU2, but we're going to focus on on these SO2 operators, where these non-BPS operators are simply the most simple things. It's just like Z's with a lot of Z's and then some derivatives. And then you have to do these permutations in order to construct a primary. But that's it. That's the operators we're going to focus. And then, what these operators have from an integrability perspective, each one of these operators is described by a set of beta roots. So it's a one-to-one map. So each operator is defined by these beta roots, which I'll call VK. And the Q functions, in usual spin chain, are nothing more than a way of packing the information of these beta roots. So they are simply polynomials that have zeros when we have a beta root. So this is true for spin chains, but for n equals 4 superunions, it's a bit more complicated. It's not it's not actually like a classical string, but actually a quantum string. So at 3-level, indeed, it's just a polynomial, which is given by here. You can see that there is a 0 whenever u is equal to k. It's a 0 when you have the beta roots. But as you go loops and loops and loops, we get non-polynomial corrections, which are these dots that I'll make more precise later on. But at 3-level, it's just that. And the only difference so far between what people usually call Q functions and these Q functions that I wrote is this normalization. with nothing more than here are the Joukowsky variables, which are defined down there. And it's nothing more than a normalization to say that these Q functions, when I evaluate them at I over 2 or minus I over 2, they're 1. But it's a normalization. It doesn't play any role, but it's here. And here, I try to do the most simple example one can have, just to demystify everything. So for these two operators, so it has z squared and then 2 derivatives. So it's spin 2. It has it's defined by this set of beta roots. It's just these numbers. And the Q function is nothing more than a polynomial that compactifies, that encodes all this information. Is this. And it's normalized, so when we evaluate at I plus or minus I over 2, we get 1. So this is, it's very simple. There's nothing mystical here. So the idea is now that we have a Q function, that is something that tells you which operator we are dealing, what can we do with this Q function? And so let me just remind you, the 3-point function we want to compute is this one. It has this geometry, let's say, so it has these bridges and these sizes. And based basically on this works here, minus the normalization constant we had to work out, we can write the 3-point function at 3 level using these Q functions just like that. So, and it's very easy to interpret this expression physically. So there is a normalization, this factorials, j factorial over 2j. So that's a normalization. There is no way to interpret this one. But then, this is up to I don't know, we just like this normalization, but okay. So then there is the numerator and the denominator. So the numerator is very simple. We can imagine that this BPS, non-BPS operator has a Q function, and then overlaps with this guy with a bridge of size L. So that's the little insert here. And this guy, since a BPS, is the vacuum, which you denote by 1. So this is the overlap of the non-BPS operator with the left, let's say. Plus, or times, sorry, this overlap of the non-BPS operator with the right. So this is the bridge L minus L. And then you have to normalize basically by the 2-point function. So we normalize by the 2-point function of the BPS, which is just 1. This is 1. And this has a non-trivial normalization, which is this guy on the denominator.
Is it invariant with respect to rescaling of Q by a constant?
By a constant. Good. Yes.
But it's
I don't know, by a constant, no, right? Because here we're going to have LQs, and here we're going to have 2 LQs.
Yeah. So that's a bit weird.
It's a bit weird.
Well, you fix the normalization by requiring Q of I over 2 equals 1, right?
Yeah.
But it's a bit strange.
Yeah, no. Let me say, like this expression, you agree with me that it's perfect, right? Like
well, I'm not sure, is it?
Okay, let me just say different. Like this expression, it has, if you rescale Q,
yes,
but some normalization, this expression here, it's invariant, right? Like
it's not obvious to me, is it?
The number of Qs, a bit more. Okay, so this L. It's written on the next slide, but okay, I will just say here. So this guy.
Are you sure there is no square root in the denominator, for example?
Is c squared?
Okay.
Is c squared? So there is no square roots. And the number of Q's that appears on top here and the number of Q's that appears on the bottom here is the same. And then you can say, okay, this expression here is normalization invariant. And then you pick a normalization, which is the one that I picked.
Yeah, okay.
And when you pick this normalization, it turns out that these 2 integrals on top are the same. And when they are the same, I can just write this squared. So from the left, so this could be like a normalization, like independent way. You can normalize the Q functions any way you want. After I normalize the Q functions to be 1 at I plus or minus I over 2, I get this expression here.
Right. So the index of the bracket does not actually indicate how many Q's appear.
They indicate. So here there is.
But then in the numerator, if I have small l equals 1, say that there are just a few Q's in the numerator.
So yeah, let me just go to the next slide, and then I think here will become more clear. So each one of these inner products here, they have this small index in the inner product L, and they are defined here. So there's a binomial, which is again like normalization. It doesn't matter much, but it's a normalization. And then you have L minus 1 integrals, and they have L minus 1 Q's. So this guy has L minus 1 Q's squared, and this guy has 2L minus 1, 2 times L minus 1 Q.
Yeah. So how come it is rescaling invariant?
So yeah, again, it's not like this
It's
expression
not,
is.
okay.
This expression is. This one is. If you count how many Q's you have on top and how many Q's you have on bottom, you can see that basically this little L disappears, and you have the way to think about this like this is basically
Okay.
2L, and this is like Q and Q, but it's okay. Like it's just a matter of counting. It's not. This is normalization invariant. This is not normalization invariant, but this is true because we picked that normalization.
Thanks. I see.
Yeah. So here, okay, and this is important. And this is the only place where the normalization enters. After you get this, like after you normalize, and then you said that these two integrals, if I overlap with the left or overlap with the right, they are the same. You fix the normalization, and then, okay, then you move forward, and the normalization is fixed. But, okay, each one of these inner products, which is written here, again, if the int L tells you that you have a L minus 1 integral, so there's a lot of Q functions being integrated against some measure. And the measure is factorized in the product of 1 and 2 particle measures. So here there is a bunch of, so there's a lot of 1 particle measures and these 2 particle measures here. And the 1 and 2 particle measures are given by this. So now, for example, like this looks complicated, but it takes 3 lines to code in Mathematica. So you code this line, and this one. And then the Q functions, you just ask for a guy that knows the Q functions basically, or take this polynomial that I showed, and then it's done. You take these Q functions, you plug in this integral, you integrate. It's integrals that you can do either by hand or Mathematica, you can do them analytically. You get a number, and this number is the structure constant when it goes for stringness, is this 3-point function.
So another
And this is true at the level. Sorry.
Another quick, can I ask another
Yeah,
question?
sure. No, I like the question.
So this 2-particle measure, normally this, if you take QQ scalar product, then you can write it as a determinant.
Yeah.
Is it the same rewriting? In this way, there would be only one measure, essentially, just mu1, and mu2 can be obtained from mu1 by some simple procedure.
In SU2, we could write stuff as determinants. Here, I believe we could have written this as a determinant at 3 level, but we didn't find a way of writing as a determinant at 1 loop.
Ah, I see.
So that's why I here present it like this, because then it gets easily promoted to 1 loop. But again, just because we didn't find it, it doesn't mean that there is not a way to do it.
What about Pfaffian? In the old usually you get Pfaffian when you write the measure in the flexible expansion or any.
I see. But that's it's another measure. Yeah.
But it can be obtained from the hexagon.
Oh, that's measured for some color stuff, right?
Yeah, but that's a different kind of. It's more natural to have determinants because you have these Wronskian relations in Hawking.
Well, no, but
Well,
I think what Ivan is saying is that you know in the end that this is a Pfaffian, so okay, maybe it's better than a Pfaffian, maybe it's a determinant. It should be possible then to rewrite its object as a Pfaffian.
Yeah, no, for sure. Okay. Actually, it's a bit different, right? Because like if you think about the hexagons, let me just say something that I was not going to say, but like I think it's important. This guy in the numerator, it's proportional to what people call the axon. So this is the guy in the numerator is basically the DVD amplitude or mathcal A, and everything else in the denominator is like the Goodell norm, basically. So if you compare this with the axon formalisms, these guys here they give the Goodell norm, and the numerator gives the DVD amplitude. So in a way, it's like a bit different, right? This numerator could be written as a Pfaffian, and the denominator could be written as a determinant, let's say. But okay, that this is not, yeah. But okay, this is the representation. I agree that at 3 level, there are several ways that we can write this stuff, even as a determinant. The whole thing we can write as a determinant. But then, as we promoted things to loop, I think this is the best way that we find so far.
Can I come back to the normalization question for a second, just for the previous slide?
Yeah.
Why is the first expression invariant?
Yeah, I think we should let's count them. Let's see. So there are L minus 1 number of Q's, right? On top, plus L minus 1 Q's, which is equal 2L. This should cancel, but it didn't cancel.
Minus L.
Oh, minus L, sorry. Minus L. So
Why minus 1?
because the number of integrals are this minus 1. So that's why there is a minus 1.
Plus one in the parentheses.
Minus L plus 1 in the second.
Ah, okay.
No.
Plus 1, no.
Minus 1. Yeah. No, it's fine.
No, in the end, sorry, what that, I did something wrong
No,
here.
I think it's good. It's L minus
So
1.
far so good, right? Okay. Minus 1, okay, minus 2. That's
Yes.
And here you have 2 times L minus 1. Which is, okay, so, no, it's not 2, right?
I would think it is, but
It's 2, right?
that's why I'm confused.
I 2 L minus 1.
Are you sure there is no square root?
I think no. I think I missed this squared actually. I think I missed this square, sorry.
Okay, maybe it's not that important.
Yeah, it's not that important, but I think I missed the square, but I don't remember. But okay, I agree that what you said now. So, yeah. Okay.
I can look in the paper.
Yeah.
Yeah, you can continue.
Yeah, okay.
It's a minor thing anyway. I'm sure it is correct in the book.
You're counting the number of integrals, correct?
Yeah, I was trying to count the number of q's. So, here will be, here's a 1. So there is, so in the denominator is q squared, right? So that's why I put the 2. Right, so I'm just trying to count how many q's you have on bottom and how many q's you have on top. And when I did this computation back home, I convinced myself it was the same. But now it appears that there is a square here, so I need at least a 2 in order to make things
Why
work.
do you want the number of q's to match?
Because I think like further ones.
No, not necessarily, but if it matched, it would be very natural because Q as a solution of Baxter is defined up to normalization.
But, I mean, is q is actually already normalized in a particular way, so I don't understand.
Yeah, right. But then if it is, then maybe there is a nice way to rewrite it so that it would be manifest. Just as
Then I guess you will have to pull out some product of q at a special point in front, and that will be
maybe, yeah, but I mean this could hint at some what is
because
the
already you know
structure
from the
and-
middle line to the from the middle equation to the last equation, it's also changing the number of q's.
Yeah.
And that's because you are using that somehow magically, or at least you expect it, but it's a bit magical here. That the overlap on the bridge L minus L is the same as the overlap.
Yeah, but this is something like this equality here, that this guy is equal to this guy squared. It's it's normalization dependent, right? Like yeah, for sure. And I think what I think in the end I said yeah, I think in the end like I'm not sure that the answer should be normalization independent, right? Like
Well, not necessarily, of course.
I think what happens here implicitly that in front of this term there is a bunch of q's of I over 2's and q's of minus I over 2's that in our equations are simply 1. So I think this will is the thing that makes
You can always write it in a normalization independent.
right. I can always write an normalization dependent. I see. Yeah, no, yeah, you. Yeah, but this. I'm just saying that okay, like. Forget about normalization. Fix our normalization. These equations are completely correct, and they give you the structure constant. And I like this normalization precisely because of that. And let me just say why I like to write this term squared and not write like this. Because when you do exigons, and you choose, when you do exigons, precisely what you get when you do hexagonalization is that the c squared is a squared divided by b. Where b is the Godin norm and a squared is what the hexagons give, basically. And if you write in this normalization, you get that this guy squared is actually the a squared. So we can make a one-to-one correspondence between this numerator and what the hexagons give. While if we do like this is not like a squared, but it's like a combination of, it's like hexagons when you rotate particles to one side times hexagons when you rotate particles to another side.
But even that is not entirely true because you have these factorials in front.
No, I'm there again, like the proper. I'm saying it's proportional. There is a lot of constant proportionality between actual numerator and hexagons, but I won't say because they're ugly actually. They're very ugly. But the good thing is that they cancel. so numerator and denominator cancel, and then in the answer, the 3-point function, in a way, it's a much more simpler object, and the hexagons and the go down are by themselves. And then we make the ratio, they become very nice. A lot of normalizations cancel. So that's why, like, I don't want you to enter like in details about the hexagons and go downs, because then things get a little bit more complicated. That's why I'm trying to like just talking about the 3-point functions themselves. And the 3-point functions at 3 level, they're given by this. And this basically minus some normalizations was derived starting from hexagons. So one can start from hexagons, do some very clever counter manipulations, and indeed derive these measures and derive these expressions. But then, what I want you to do, basically, is try to derive this result, derive this 3-level expression for the structure constants in a different way, right? And when we do this derivation, perhaps we can generalize to higher rules. And, okay. So the guiding principle of our derivation is what we call orthogonality. So it's basically, the physical idea, it's kind of simple. It's like, forget a little bit about 3-point functions, and let's just look at properties of 2-point functions. And we know that if we consider 2-point functions of 2 distinct operators, they must be 0 somehow. They must be proportional to some delta function. So our question now becomes a simple question that we can say, that let's search for measures that when I fix some size, I fix some speech n, and I consider 2 functions that have that describe 2 distinct operators that are proportional to the delta function. Perhaps the measure that arises in this as the answer of this question could be used to build the measure that we use to the 3-point function. Could be. Let's see. So let's ask this question for the most simple case there is, which is when we have twist 2 operators. So the size of the operator is 2. And then we want to do a 2 minus 1 dimensional integral. So we want to do just a single integral. And the single integral that we need to do is precisely this. So we have a single integral, an operator of spin j, an operator of spin j prime. And then there is this measure, which is the one particle measure. And we want to fix this measure, so we have orthogonality. So that's the question we want to answer. It's a very simple one. And then we can derive this measure in 2 different ways. The first way is that these 2 functions of twist 2 operators, they can be written as Hom polynomials. So they are the solution of the Baxter equation. You can write them as Hom polynomials. And then you can use it, which is nothing more than just a fancy way of writing hypergeometric functions. And these hypergeometric functions, they have orthogonality of their own. You can just go to a mathematics notebook, and then look at the orthogonality of hypergeometric functions. And indeed, you can derive this. You can derive just by looking at this orthogonality. But what I will do in this derivation that I will do, it's a bit different. It's just using the Baxter equation or just using some integrability constraints, because then we can do a one loop much more easy. Okay. So let's try to do orthogonality. So let's try to find this measure. And let me just remind you that at 3 level, we know that the measure is given by this. So it's pi over 2 divided by cos squared. Okay. So let's look at the Baxter equation. What's the Baxter equation? It's given by this at 3 level. So there is a linear operator that acts on the Q function and gives us the transfer matrix. It's just, I think, another polynomial times the Q functions themselves. So this is the equation that this Q function satisfies, where this Baxter operator is just a linear operator. It's given by this. So there is this u plus I over 2 to the power L, or in our case, L is equal to. And then there is this derivative, which is nothing more, which is the only thing that it does is that it shifts the argument of the Q function. So we're going to have 2 of u plus I over u plus I. And then there's the same thing with the complex conjugate. This, for twist 2 operator, the transfer matrix can be written like this. So there's this polynomial and then a constant that depends on the spin. And then we can just look at the following combination, a very nice and straightforward combination to look. The Baxter operator acting on the Q function with spin j times the one with j prime, minus the same thing but I switch j and j prime. So this is the combination that we want to see. And if you see, if the left-hand side is 0, we get our orthogonality, because if j is different than j prime, this constant is not 0, so the integral must be 0. If j is equal to j prime, this constant cancels, and then the integral can be whatever you want. So in other words, we want to make the B a self-adjoint operator, or just in a more nice way, just say we want to make the left-hand side 0. And to make the left-hand side 0, it's very simple. We just can write explicitly what these integrals are. So these are wrote explicitly. So this is the first term of the first integral. So this is 1 plus I over 2, you can already see here. And this is the second term of the second integral. Right? So there is this measure, there is the minus I over 2, there is this minus I, plus the complex conjugate. See? So this is the full left-hand side. So far, clear, right? And then we just make a counter. We just make a counter shift. We just make u goes to u minus I, and this is what written here. It's the same equation. It's just written here. If when we send the counter when we make this counter manipulation, we do not pick any extra poles, and there are no problems of infinity, this is the only term we get. And they are the same if this measure is I-periodic. They will just cancel, and then we get 0 to the left-hand side. So this is precisely the things that we want to ask for our measure. Our measure must be I-periodic, cannot have any problems at infinity, or must decay fast enough at infinity, and there are no extra poles when I change the counter from u to u minus I. And this is precisely what's written here. So this measure must be I-periodic. You can write like the combination of Cauchy squares, let's say. It must decay fast enough at infinity, meaning I can integrate against any polynomials, because these Q functions are polynomials. So it must be non-negative, or non-positive, sorry. And then it must have no extra poles when I make these counter manipulations. And we see Cauchy squared has a double pole, but this guy has a double 0, and they will cancel precisely. But Cauchy to the 4, Cauchy to the 6, and all the other Cauchys will add extra poles, and then we will get extra terms here, and we will not get 0. So then in the end, you fix the measure to be just this. Orthogonality fixes the measure to be just this, which now we can just normalize by the vacuum. We just say that the integral when I have no Q functions basically is just 1, and this gives fixed pi over 2 here. So now we're done. So it's and this is something that is very important. We asked orthogonality, and then we got the measure that people use to compute the 3-point function. So apparently, asking for orthogonality gives you the correct measure. So then we can ask the same question. Now that we know orthogonality at 3 level, can we ask the same question? Can we ask orthogonality at 1 loop? And then perhaps we get some measure that we can use to evaluate the 3-point functions.
So the 3-level thing, this is what was in our paper, right?
Here. Sorry, it's I think it's that one. Yeah. So yeah. Right. So yeah. So far this orthogonality is perfect. Yeah. And then we can go at 1 loop. And at 1 loop, we have the Baxter operator, which is written here in an unorthodox way, but it's the same as you're used to it. It's just that the Q functions, they get this Baxter equation, which now is written here. The same thing is Baxter acting on the Q functions, the transfer matrix times the Q function. So this is the same thing. It's like the Baxter operation gets shifted in 2 ways. It gets shifted via the Joukowsky variables, and via also the change of the S matrix, which is just basically this term here. So we have a G squared plus something that depends on the charges. So these are the conserved charges. So it's just a combination of theta roots. For example, the Q of Q1 plus. Am I correct? Yeah. No, sorry. That's okay. No, it's there's something strange here.
It's just some detail.
Okay, but it doesn't. Q1 plus is basically the anomalous or the energy of it's the usual energy. It's just a way of writing the energy. But the problem is now that this operator at 1 loop is not a linear operator anymore. It depends on very non-trivial on these beta roots if you expand at 1 loop. And then it looks like that we are in a bad spot, because we want to do the self-adjointness. We want to make this combination and do the self-adjointness at 1 loop, and now it's complicated. So then the solution is basically let's try to search for a Q function, which is it starts from this, but it gets this mathcal K. Let's try mathcal Q. Sorry. Let's try to define a Q function such that the Baxter operation, or the Baxter equation, becomes like a linear equation. And then it turns out that this very ugly combination, so this Q function times this thing, where now this is the charges, and this is just some combination of harmonic numbers. So this is the combination of harmonic numbers. So this function of U and the beta roots satisfy a linearized Baxter equation. If I act with this operator, which now is just the Joukowsky variables, basically, and the shifts, it satisfies this linearized Baxter equation. So that's the idea. And now it's very simple. Now we can just make the same combination of Baxter applying on Q of j times Q of j prime minus the same thing swapped, and then ask, can we make this combination self-adjoint at one loop? We expand everyone at one loop, and then we shift the counters. And then what happens when we shift the counters? We ask the same questions. We cannot have any problems at infinity. It must decay fast enough at infinity. We cannot introduce any extra poles. And then this completely fixes this one particle measure. Completely fixes this one particle at one loop. And it fixes the one particle measure to be this. So this is the claim. If you consider twist 2 operators, so namely, if you replace these VKs by any twist 2 operators, any twist 2 beta roots you want, and then you consider the orthogonality of this with any other solution you have, with this measure, it will be proportional to the delta function at one loop. Not only at the level, but at one loop as well.
By VK, you denote the full beta roots or the tree level?
The one loop. So you need to put the one loop beta roots here. You expand everything at tree level, or at one loop. You plug this measure. You do this one integral, one-dimensional integral. You're going to get either something that is non-zero when they are the same, and something that is zero when they are different. So you get this orthogonal measure.
Can you show the stage recursion again?
Sorry. So it's just this harmonic numbers with minor, yeah.
Do you know what is this function in terms of the quantum spectral curve?
Good question. Yeah, as I was anticipating this question actually. So the answer is no, I don't know. I know.
Well, I have a suspicion that I just never.
Yeah, I know that like I think Frank told me like part of this answer like by memory, but I can recall it, but I'm not 100% sure. But I remember there is a Q function.
Probably Q12/12.
See, yeah, it's the one that I told you. So it's Q1. I think it's Q12/12. But I think is that function is squared, because if you look at that function, it doesn't have this 1/2. So apparently this I think is that function, but it's the square of that function. But I don't know. Yeah. And
if you square the function, you will also square the polynomial.
Yeah. It's the one. It's sure. So it's not squared. It's just this. Yeah, for sure. It's not squared. It's just it has here I think it's 1/4 and ours is 1/2, or ours is 1 and ours is 1/2. I don't know each side is the factor of 2. But I think your the ones the quantum factor the one in the quantum spectral curve is 1/4, if I remember correctly. So yeah, no idea. And you see, it's kind of a different game, right? It's almost. Right, it's a strange combination. So
the problem is that at the next order, there is some more weird stuff appearing.
Yeah, the next order, I prepared a bonus. Yeah. I will not present until the very end, and then I put in a bonus slide if there is questions. But so far, I will skip that one. But now, okay. So now we have, so let me just recap. We have a Q function, which is defined like this. We have a measure that is defined like this. And this is orthogonal at one loop. At the level, we saw, so let me just recall what's the structure constant for twist 2 operators. It's given by this, where now the size of the bridge is 1, and the size of the operator is 2. So since this is a L minus 1 dimensional integral, the numerator is a 0 dimensional integral, so there is no integral to be done. And the only integral we need to do is in the denominator. So the 3-point function for twist 2 operators is given by this. Very explicitly written right now. And we know that this is true at the level. If we take this measure and this Q function at the level, this is true. This is derived. At one loop, we can just ask the same question. If we now take this one loop measure, this one loop Q, and plug it here, do they reproduce the 3-point function? It's a completely finite question. And then we do it. And then we see that it does not. And in fact, there is a small prefactor missing. And then we start looking for this prefactor, and we found it's just this. So we need to send this spin to basically this spin goes to G squared times gamma over 2, times the anomalous dimension, basically. So once we make this, then everything is correct. Like we can assume that we can find this prefactor for the first 1, 2, spin 2, 4, and 6, let's say, because it's easy to fix this prefactor. And then we can just compare with accident for spin 20, spin 10, spin anything we want, and then we always get the same answer. And then we're pretty confident that in fact this prefactor is correct, like it was not derived, but it was found, and it's a very trivial uplift of the twist to solution to one loop.
You don't have any wrapping so far, right?
No wrapping so far. No wrapping. No wrapping. Wrapping only appears at 2 loops. And then, now that this is true, now that we checked by exhaustion that this is true at one loop for twist 2 operators, let me just claim the following: that this is true for any twist and any bridge length at one loop. And then we use the Q function at one loop is given by this. The one particle measure at one loop is given by this. And then it comes the 2 particle measure. We never fix it. We never fix it. We didn't derive it. The only thing we derived via orthogonality was these 2 things. And then we did the following thing. Let's assume that this is true. And then we look at the 2 particle measure, because now if I put like twist 3, for example, this 2 particle measure appears. If I put bridge length equals 10, this 2 particle measure appears. And then let's just assume the most simple thing we can imagine, because this guy got shifted by tangents. So let's just assume tangents here. That's how we did. It was guesswork. There was no derivation. We just assumed tangents. And then we assume like 5 tangents, like tang of pi u squared, tang of pi u times pi v, and so on. We assume these tangents, and then use like 5 or 6 beta roots to fix, to see if it was true. And then we fix the coefficients. After these 6 coefficients are fixed, we then checked up to twist like 7, and bridge length equals as much as we can. And then after these dozens, almost like 100 coefficients were the same, we said, okay, it's true. But it was not derived, but up to our standards was checked by exhaustion.
Do you have any understanding of what procedure promotes mu1 to mu2? The one loop. Okay, so at tree level it's the determinant thing, but
okay, yeah, at one loop, no idea, no idea. Yeah, and also there is, yeah, okay, yeah, there is some.
well, I mean, it's very nice that it works this way.
Yeah.
But certainly there should be some way to understand.
For sure. That's the problem. Like what I will present is something that works at one loop, and some results at 3 and some results at 2 loops, and but then we are still lacking like all loop interpretations, how to go to higher loops. But it's just like the beginning of I think with a nice prescription. But the beginning is this one. And this is a very, very nice claim. And this is basically what I said in the beginning of our goal was to have like an easy and powerful way that you can compute this structure constant. So it's very simple. Like it's 3 lines of code. Like Q is equal to this, mu1 is this, mu2 is this. This is L minus 1 dimensional integral, big L minus 1 dimensional integral. You can do all the integrals even at one loop analytically. You can do them in mathematics, or if you're crazy, you can do by hand. But then in the end, you get a number. And this number is precisely the structure constant at one loop. Now, let me see, what time is it? Okay. So now I have like 3 orthogonal directions that I will try to say. If there is not enough time, I can just jump the last one or some of them. But it's now that we have this result that works at one loop, we can ask questions in these directions. For example, what if you want to go to higher loops? So and then wrapping appears in the accidents. The other question is, what if we consider a 3-point function not of just one non-BPS operator, or more non-BPS operators? And the last one is, which I don't hope to skip because it's one of my favorites, is like what sort of limits are nice that we can take in this new formalism from an integrability perspective. And then I'll try to tie everything together in some final remarks, but let's see. So I think that's, I'll not skip this one because I was already asked. It is about wrapping, but it's a lot of stuff to talk about two loops. So I'll just try to say what's like the two physical ideas that appears at two loops, basically. So first of all, let me just say what happens, forgetting about SOV, what happens from in the 3-point function. So the 3-point function, let me just remind you, is this one. And what we will study is the most simple example, is where when this non-BPS operator is twist 2, meaning it has only 2 lines coming out of it. So this bridge L is 1, this other bridge is 1, and then there is this L bottom, which now it was just a spectator. It didn't play any role, neither at the level nor at one loop. But at 2 loops, this L bottom matters. In fact, if this L bottom is 1, we have wrapping. And if L bottom is not 1, this wrapping is delayed at 2 higher loops. And just saying, I think like 99% of the audience know what wrapping is, but like just in a nutshell, is that when you do the hexagons, we break this 3-point function. We break this pair of pens into 2 hexagons. Then we have to sum over all the way that we can distribute the excitations of this operator between the 2 hexagons, and then you have to glue back the hexagons together. If you glue by the identity, it's okay, but if you glue by some mirror particles, let's say, you have to sum over the momentum, and basically these mirror particles are the ones that do the wrapping stuff. And as I said, from this hexagon formalism is there are 2 very distinct objects. There are 2 very distinct objects. One is like a sum over partitions, and the other is basically an integral. But if we try to take this expression that we have from hexagons and try to write it in a SOV type of formalism, namely, try to write the answer that the hexagons gives us in terms of some integrals times some 2 functions, we find the following. So here I just wrote the numerator. So I forgot about all the normalization, the Godel norm, and everything else. This is just the numerator. And the numerator is given by this. So this is what we obtain at 2 loops.
What is new?
Yeah, I forgot to write. But it's the usual measure that appears in wrapping. It's something that is completely known. It's like some tangens times something. It doesn't matter much. But I'll just skip the slide because the expression is here. So at 2 loops, we get this. And then let me just analyze the 2 key ideas. That's why I'm presenting this expression. So the first key idea is that, as was also observed before, this integral, this inner product, has the index 1. So it should be a 1 minus 1 integral. So it should be a 0-dimensional integral, so it should be a constant. And indeed, at 3 level and at 1 loop is a constant. But at 2 loops, it's a 1 integral. So we start to see that the number of integrals is beginning to grow. And I think this is like some very physical idea that was also previously anticipated in the past. Is that as you move forward in loops, you're not describing really like a classical string, but a quantum string. So it has infinitely many degrees of freedom. So in the all loop way, you should have infinitely many integrals if you want to do it. So that's just saying that as you go higher and higher in loop orders, it's expected that the number of integrals should increase. Because in the very core, the integrals are just counting the degrees of freedom, and you start to see more and more degrees of freedom as you go. The other thing is that in the hexagon formalism, asymptotic and wrapping are usually very different. And when you write in terms of 2 functions, the 2 of them combine in the same expression. So you can already see that they all combine in this eta here. If eta equals 2, so we have wrapping. So we have asymptotic plus wrapping, give the same integral, so we have a factor of 2. If we have LB plus 1, we do not have wrapping, and then we have just a factor of 1. So in this way, when you try to write everything in terms of 2 functions, wrapping and asymptotic get combined in the same factor, which is nice. So, yeah.
I find it a bit confusing what you are saying, because the hexagon description, the physics in the bottom channel is totally factorized. So you could, for instance, it has in principle nothing to do with this adjacent channel and so on. So you could say there is a piece of the answers that take care of this Mat-Calais and correction to it. And there is another piece which is just like bottom channel integrals, the one you just shown before. You can factorize it. And they don't talk to each other.
Yeah.
So I think here what you call LB is not really LB. I mean, it's more like what is adjacent. Yes. And when you say that the physics depend on the length of the bridge, you mean the bridge of the adjacent channel.
It depends on the two bridges, right?
Yeah, but the other one is factorized. So why do you want to modify Mat-Calais?
I see.
I think you want to say that in the spirit it is an integral similar to the one you have for the bottom channel, but it's actually not the bottom channel integral. I mean, it's not describing the physics of the bottom channel.
No, but there is an integral that depends on the bottom channel, right? Like if this bottom channel is 1, there is a wrapping integral, right? There is bottom wrapping.
1 plus first integral plus double integral and so on, but everything is factorized. So not something a priori that you want to absorb in this overlap that you mentioned before.
No, I see. It's just, okay, so I agree. Yeah, it could be that, I'm just, the punchline that I wanted to say, I see. You could say that the overlap could still be 1, and then it's factorizing something else that we could call wrapping, right? And you're just saying that, okay, yeah.
I just
No,
don't
but it's
understand, because for me it's totally factorized. So I don't understand. Are you trying to absorb it elsewhere, or you already have this integral in front of everything, like 1 plus an integral plus a double integral plus etc. So I'm not sure I understand how you are absorbing it here. It's
So yeah, if you're doing hexagons, you would write asymptotic times wrapping, right? That's what you're saying, right? Or
I'm saying
because
that
if
for this
it's 10.
specific channel, which is LB, actually all these wrapping corrections are completely factorized from the rest. So they don't really talk to each other. I mean, they depend, of course, on the state that you are inputting, but they are not like entangled with the bridge overlap on the left or on the right, what you were considering before.
I see.
So they are not really entangled. I don't understand why you are trying to absorb them in these factors.
I see. Yeah, no, okay. I agree. I think the punch. Okay, this could be a bad way to repack the whole. I agree that this could be a bad way to repack the whole answer. But I think that what I wanted to say is that if you compute the asymptotic part in the hexagon, and if you do it off shelf, it's like Bernoulli numbers times beta roots. If you expand in terms of beta roots, it's like some Bernoulli times beta roots. If you compute wrapping, it's like an integral. But if you try to write all this complicated stuff that the hexagons gives of the asymptotic part as some Q functions, you get the same integral. That's the only punchline that I was trying to make. And then, like, combining the two integrals, okay, could be misleading because they indeed are factorized, and then I agree.
So just to make sure, so this LB here, when you say LB is greater than 1 or is equal to 1, are you talking about the small L? Which
No, this L is this is always 1. This is always 1. So this L is this L over here, which is always 1, because I'm looking at these two operators connected by a bridge 1. And then there is LB. LB could either be 1, 2, 3, anything it wants. And this 1 that is written here is the bridge. And now, but this 3-point function depends on LB. At the level at one loop, it doesn't depend on LB. LB can be anything it wants, and this 3-point function is the same, basically.
I understand, but so the way I will think about it is that I take two structural constants, one with different value of LB. If I take their ratios, the dependence on LB disappear completely. Oh no, sorry, I take one of them with LB which is infinite, and another one which has whatever LB you want, and then I can factorize the dependence from LB from there. Sorry, I'm not sure if I'm being clear, but yeah, I'm not sure I understand the logic of this.
Because
I personally don't understand the notation. So previously the bracket was an integral. Now you say replace the bracket by 1 plus integral. What do you mean?
So my question is, when you are writing this overlap of you cut the chains in pieces and then start to write the overlaps. So in the beginning, the bottom piece was trivial because you imposed so you just removed it from there. It was 1. So I thought this is the piece that you want to correct now when you write the wrapping correction. So yeah, I have a bit the same confusion as. I thought. I mean, if you start to correct entire loop, you will see something also in this piece. So.
The way that I think perhaps is a wrong one, but the way that I think is that in the beginning I was writing this sort of overlap with 1. I mean, this is just a small l. But I believe this overlap depends on all the geometry of the 3-point function. Depends on L, LB, and so on. But so far, at 3 level at 1 loop, you never knew what LB was. So like it was, you didn't see this dependence, right? Yeah. So I'm just saying that, yeah, it should be an extra index here, like 1, comma, LB. And then, yeah, I don't know. But yeah, I think I'm missing the question actually.
May I try? So you have an inner product, right? Which you write bracket. Okay? And now you're kind of deforming it into a new inner product, which is the sum of the previous one and this new integral.
Yeah.
Right? So on the right, it's actually the inner product of Q with 1 with respect to this second piece of the measure.
Yeah. Yeah.
Okay.
Yeah.
So it should be Q1 goes to Q1 before plus this integral. Is that right?
Yeah. But again, like we didn't. Like we just okay. This the problem is this is not a claim of what will happen when you have general twist and general else. And I think that's the problem. Like we're trying to repack this in the general expression. And I think like this is a very, very small an observation about what happens when you have twist 2 and bridge 1. So before we had 1 in the numerator, and now we have an integral in the denominator. And that's just to get a flavor what will happen if we go to if we consider general stuff, perhaps these Q functions will happen precisely that. These inner products get promoted to the inner products plus an integral with another inner product. And yeah.
Okay, so 1 is the value of the bracket. Which
one is really the value of the bracket because this is when this bridge is 1. This is a zero-dimensional integral. I don't want to make any claims when I have L here or when I do not have twist 2 or anything else. I'm just trying to say because we were not able to find this stuff at 2 loops for any bridge, like for any bridges or to write wrapping for anything we want. We just went to the very most simple case possible, which is like twist 2, everyone has bridge 1, and then we saw what was happening there. And then this is like an inspiration of what should happen perhaps when we go to higher loops.
Okay, just this constant is 1. Can I think of it as the evaluation of Q at I over 2, for instance, or something like this?
No, rather
in linear form here. I need an inner product, right?
I think it could be.
It could be like I don't know. Okay.
But just to be sure, this so this integral you wrote it a bit schematically here, but is it literally the same as the same integral as the one we have in the bottom channel, like the sum over all the speed integral of the measure and so on, or it's different?
I think it's a bit different, but but it's the same that appear. Yeah, I should have written here, but it's in the paper. I should have looked it up. I forgot to write it. But it's the same integral that appears when you are doing like pure wrapping. If you forget about any SOV business and then you go to wrapping, is the one
because if it is the same, I think what I would naturally do is to actually divide by this contribution from the bottom channel. I think that will remove 1 unit of eta.
I see. I said, no, but
Then you are just saying that, okay, there are situations where you get actually.
No, I agree. That could be the way that this thing gets generalized if we consider high like other bridges or other stuff. But I think like that's why like I think I should have. My plan was actually to skip this first orthogonal direction because it was a bit too schematic and I didn't want to present too much details. But I just like find it nice that we were observing that indeed this physical idea that the number of integrals was looking to grow, like it was starting to grow. And I think this idea is a very physical one, and yeah, that's why I decided to talk a little bit about it. But I agree that I should add like 3 or 4 more slides with formulas in order so we can talk properly about this thing. Yeah, but okay. Sorry, yeah. But there was just like very small explorations that we were doing in wrapping, and just like seeing, yeah, we do not have a full picture of what's going on at two loops, and indeed we are trying to search it, but it's kind of strange, and things are not as nice as they are at the moment. But at one loop, let's see how much time I have left. Very few. 5 minutes, okay. Okay, so at one loop, I would just like to say that if we consider more than one operators, we still have similar formulas. So I'll not get into detail, but you can already see that if we consider spin 1 and spin J1 and J2, we can write one loop expressions for a structure constant like that. So indeed, this SLV formalism seems to hold not only for one spinning operator, but for more.
This is SL2 still.
This is SL2. There's 2 operators and SL2, and furthermore, they are polarized in orthogonal directions, right? They are not polarized in arbitrary directions. And I think like one nice thing that we can ask about this new formalism, which is something that is very complicated to ask for hexagons, for example. In hexagons, I'll just be very brief about this one. But in hexagons, a very complicated thing you can ask is what's the large spin limit? Because the number of sums that you need to do grow with spin. And if you want to consider, for example, spin j, you have 2 j sums, and so on. So it's very complicated to do, especially for 3 spinning operators, which is the thing that I most want to understand. But from an SOV perspective, the only thing that matters for this SOV is the size of the operator. So it's the size of the operator and the size of the bridges. So if you consider small operators like twist 2, twist 3, twist 4, you have like 3 or 4 integrals that you need to do, but then you can send the spin to be anything you want. So this could be a window that you can look to large spin limit in the hexagons. And perhaps understanding how this large spin limit connects with other integrable objects, like the integrable pentagons. And I think this is like the most, like for me, exciting upshots of this SOV stuff, because it opens this corner of large spin integrability, which is very tough to do with our current tools. And yeah, with that, I will just conclude that for SU2, which I said basically nothing today, we also have similar formulas. And they are nice because they are through a 3-level, 1 loop and 2 loops. And then at 3 loops, we start to speculate, just like I did for our SO2 case. But here, it looks like that's looks like large spinning, but like large spin is one thing that we can do with this formalism. But here, for SU2, which a limit that people like to take, like large operators, let's say, seem to be a very complicated limit, because then the number of integrals goes to infinity. So this looks like not the nicest place where we can look for again, but this is very, we didn't explore anything, but in principle, just from a naive perspective, seems to be the most hard limit that we can study. And and now we are just trying to, we focus on rank 1 sectors, but then we can ask for higher ranks. So not only SL2 and SU2, but perhaps general solutions. And I believe that if we ask for like more rank sectors, this also shine lines into what happens when you have more than 1 non-BPS operators, like 3 non-BPS, which is the thing that I like. And yeah, perhaps some all loop expressions will be nice. And we want to understand if these measures that we start to derive at 1 loop and 2 loops, if these measures, they obey some underlying guiding principle or some try to bootstrap equation or something, that in the end we can use it to find it at the higher loops and so on. So yeah, thanks a lot.
On the previous slide, can you show for a second? Well, I just didn't see. The number of integrals does not grow. Okay.
Yeah, does not grow with spin. So yeah.
Also, I wanted to complain. I will be honest about it. It may be useful to mention our paper with Kolya and Andrea, where we computed the correlator of 3 cusps.
Okay.
Several years ago, and we found exactly the same kind of structure, where you have scalar product of q's and then divided by norm of q's. The situation is very different there because it consists entirely of wrapping corrections. Well, here you have mostly asymptotic results, but still it's the same answer. And that's, well, I think this gives further hope that this all can be promoted to actually work.
I see. No, yeah. And there you have also like 2 cusps and
well, we had the 2 heavy light.
Okay.
Well, if you wish, you can take heavy light. So 2 non-BPS and 1 BPS.
Yeah.
Well, the structure is almost exactly the same.
Yeah, no, for sure.
We had the length 1 in a way only, so we don't have multiple integrals. But otherwise, it is just like this.
Yeah, actually.
And also Shota and Simona Giombi, Shota Kamatsu and Simona had a similar result in another.
Yeah, the main motivation for me to work on this stuff is actually to, in the future, to take large spin. Like, it's something that I like, and it's something that that I'm currently thinking about it.
Also, another comment for the last slide. So you mentioned what happens when we consider large 4-point functions. So do you mean some paper of Frank, which is in preparation, or which is?
No. I shouldn't put the large here. I just forgot. 4-point functions. So, so I just want to say, like, when you do hexagons, you hexagonalize this 4-point function, then you have to sum over intermediate states, let's say. And I'm just saying, like, if you try to think about this in like a Q function perspective, what you're doing, like, are you summing over intermediate Q functions? Like, it's just a speculatory comment. And if perhaps we can make this more precise, could be a way that they can rewrite or rederive or reobtain some limit of the octagon. But
and for 3-point functions, you don't have the sum of the intermediate states in the same spirit as for the 4-point.
It depends if you consider wrapping or not. Like,
yeah, but I thought that it was roughly the same. No? Or is it qualitatively different in some ways?
No, but it's, yeah.
Well, there are more hexagons, of course. There.
Yeah, it's
not just 2. And thanks for the nice talk.
Yeah, there you go. Yeah.
Okay.
I'm trying to understand the logic. So at some point you had a Baxter operator which was complicated, and you sort of took the complication out of the Baxter operator.
Yeah.
So functions H. Was H is and there was some relation satisfied by that, but not functions.
H is a very concrete function.
It's a harmonic number. Yeah. It's just a harmonic.
There's an actual formula for it.
Yeah. It's age of, actually age of n.
Yeah.
Oh, sorry. Age of n. This is big N, and this is n. So they are defined for anything.
Oh.
So yeah.
Well,
So the age,
but
Yeah. For example, harmonic number of one at infinity is like.
Yes, okay. Very good. So these are just coefficients.
Yeah.
Coefficients in our.
they are also the anomalous dimensions of the state.
Yeah.
Physically.
Yeah. Yeah. And also,
But
yeah.
the idea is that you, in your Baxter operator, you find some state